So my today's session is on curve fitting, and here I'm going to discuss general curves, some general curves other than linear or second degree parabola, and specifically I shall be discussing the curves of exponential type, logarithmic type, and power curve. Exponential curve and logarithmic curves are very important for this topic of curve fitting, and it always most of the time we actually use them. Power curve is also very important, but other than these curves, exponential, logarithmic, power, there are some other curves. Let me name those, like logistic curve is there and Gompertz curve is there. So various other curves are there which can also be fitted, but we don't have any the discussion of those curves is beyond the scope of our syllabus, so I'm not going to get into the details of those curves. We shall only stick to exponential, logarithmic, power, second degree parabola, and linear. So I shall start my today's discussion on fitting of exponential curve. Before I start, as the student has asked me a question that during the examination he or you will not be having access to Excel, how will it be possible for you to analyze the curve or to find the curve of best fit? The answer is if it is a matter of examination, then you don't have to worry much, because in examination the question setter will ask a particular type of curve. He will ask you to fit a particular type of curve to a given set of data, and you don't have to analyze. This is not analysis. This is kind of a question is given and you are going to give the answer without knowing whether it is a best fit or not. So it is not a writing answers in the examination is not a practical analysis, so you don't have to worry much. For practical case, what you need to do, I shall discuss gradually as this particular class proceeds on. I shall come to this particular point, but before that, let me begin my today's topic, today's session, with the fitting of exponential curve. And as usual, for fitting of exponential curve also, I have to deal with the bivariate distribution into variables capital X and capital Y, where one variable will be response, another is input. It is a matter of choice which variable will which is what. If, for example, you can consider any of the two variables to be input and response. The other one is response. I've already discussed it. The important part is, if it is a matter of fitting exponential curve to a given set of data, then you have to select or you have to assume an appropriate equation for doing that, and that equation is represented by the exponential equation will be represented by the equation given in 1. See the form of the equation. It is capital Y is equal to small a multiplied by exponent of b multiplied by capital X, where small a and small b are the parameters and they are unknown. We have to analyze, or we have to take the help of something, and that something is the normal equation, to analyze and to get the values of these unknowns, small a and small b. And for the time being, we shall assume that for the given problem, this exponential curve fitting is possible. Okay, but the problem is, when we discussed about normal equations, if you can remember from our earlier classes, that normal equation can be built upon a linear type of equation. So we had equation like y equal to a plus bx, and also we had equation like y equal to a plus bx plus x cx square for second degree polynomial, where we fitted the normal equation. The most important part is the thing can be linear or non-linear, but there was kind of a plus sign between the two terms, a plus bx for linear and a plus bx plus cx square for non-linear. But here no plus sign is available. Here the product is available, product of the exponent with the constant. So directly you cannot fit the normal equation to the you cannot set the normal equations to the given equation 1. Okay, you have to bring it to that form, something plus something first of all, and then only you can fit the you can set the normal equations accordingly. Okay, so step number 1 for this fitting of exponential curve is to take logarithm on both sides, so that we can get a term like this: log a plus bx into log e. So if I take the logarithm of this right hand side, you know, log of xy is equal to log x plus log y. So we get something plus something form. Okay, then only we can set the normal equations to the following. Now, logarithm can be calculated to the base or to the arbitrary base. You can take the logarithm to the base 10, logarithm to the base 2, logarithm to the base e. Here in this particular case, for exponential curve fitting, since here exponent e is present, so it's a natural choice. The natural choice for logarithm, or natural choice of the base for the logarithm would be e. So that when you take the natural logarithm on both sides, log of y, log a, and it becomes bx into log e to the base e, and log e to the base e becomes 1. So we get this type of equation: log y is equal to log a plus bx. So you can now say that in the equation 1 is a linear equation, the exponential equation, but log y is equal to log a plus bx is a linear equation in terms of the variable capital X and log y, because the power of the variables log y and capital X is 1. Okay. Now, to keep the parity with the notation of the earlier forms, which was discussed in the earlier two classes, the log y has been written, the term log y has been written by with the help of the notation y star. And in place of to keep parity with y star, I have named capital X, the variable capital X, to be x star, so that I can say that this equation is a linear equation in terms of the variable x star and y star, for the sake of doing calculation. Log a, the natural logarithm of this parameter small a, is treated to be noted as capital A. And to keep parity with this parameter capital A, I am renaming small b, the parameter small b, as capital B. So we get capital X equal to x star, small b becomes capital B. So there is actually no change in them. But log of natural logarithm of small a is equal to capital A. This is my renaming, and natural logarithm of capital Y is your new variable y star. So ultimately, after doing this, we get a linear equation in terms of the variable x star and y star, as y star equal to a plus b x star. Now you see, it has taken the well-known form of and it's a linear type, and we can very well set the normal equations to it. Okay, as just like we did earlier. So your step number 2 is to operate summation on both the terms, on all the terms present on each side, and so that we get summation y star on the left hand side, summation a on the right hand side, plus summation b x star on the right hand side. B is a constant quantity, it comes outside, you know, and it becomes n into it becomes b into summation x star, and a is constant, it comes outside the summation, so it becomes n times a. So summation y star equals to n times capital A plus b times summation x star becomes your first normal equation, represented in equation 2. After this, we need another normal equation, because we have two unknown parameters, capital A and capital B. So to do this, just like we did in the previous case, we shall multiply these two by x star. Previously we multiplied by capital X, now we are going to multiply by x star. Actually, what happens is that we multiply by the input variable. First of all, if it is a matter of two variables, we multiply by the input variable. If it is a matter of three variables, we multiplied by, first of all, the input variable, and then by the square of the input variable. Just like we did in the case of second degree polynomial, where we first multiplied by capital X and then we multiplied by capital X square. So here my input variable is x star. So we are going to multiply by x star. Both the sides, we can multiply all the terms present on both sides of this equation. And then you take summation on both sides. You operate sum on all the terms present on the sides of equation. And we get summation x star y star equals to a summation x star plus b summation x star squared, represented in equation 3. So this green colored equation present in 2 and 3, these are the normal equations with respect to the linear equation y star equals to capital A plus b x star. And now my job is to solve the equation 2 and 3 in usual method and to find the value of the parameters capital A and capital B. But you have to keep in mind that to fit the exponential curve y equals to a e to the power bx, we are actually not interested about capital B and capital A. Although capital B is same as small b, but you have to keep in mind that our actual parameter is small b. So when we solve equation 2 and 3, we get capital B, which exactly is equal to small b. So that purpose is solved. But when you find capital A, you have to keep in mind that capital A is actually the natural logarithm of small a. And therefore, from there, you have to calculate the value of the parameter small a. Since natural logarithm of small a is equal to capital A, so small a will be the exponent of capital A. And once you get the values of the estimates of the parameters small a and small b, then you can put them in the equation 1 to get the exponential fitting. So let us proceed with the problem. Problem number 1 says the following data represents the count rate of radiation particles versus the thickness of aluminum shielding. Aluminum thickness is given in centimeter. These are the values, and count rate of the radiation particles, count rate per minute, are given here. There are 6 observations. Fit an exponential curve to the above data. Now the student has asked me, he will not be having, or nobody will be having access to Excel or any kind of software to deal with this type of problem. So how can he measure the best fit? How can he quickly check the scatter diagram and the best fit? Now if it is a matter of examination, then obviously it is not possible, because the authority will not give you the access to the softwares. Okay, so I shall, if I consider this problem number 1, this is a problem present in the question, and already the question setter has asked you to fit the exponential curve, then you have to believe him, that he thinks that the fitting is possible, and he just wants to know whether the student knows the technicality of the problem or not, or technicality of the fitting or not. So he's just checking the technical capacity of the student, but he is not actually judging the analytical capacity of the student. If I show this particular process to any group of students, he or she may not be an engineer. Anybody, after seeing once or twice, can solve this particular problem without understanding a little bit of what is happening, because he doesn't know the analysis. So if it is a matter of examination, then you have to believe the question setter that he thinks that exponential fitting is possible. You have to just show your technical capability, and you have to find the exponential curve. But if it is a matter of practical problem, if it is a matter of practical scenario, suppose I am asking you to find to fit some sort of curve to the given set of data, I shall never mention that fit this and that curve. I shall never ask you fit linear curve or fit exponential curve or fit Gompertz curve or fit logistic curve. I'll never say. I'll say fit a curve which is best fitted. So that is called analysis. And then we'll have to, in practical scenario, when we'll be dealing with some sort of research problem, or in some sort you are doing some sort of you are analyst in a particular company, then you'll be having the access to the various softwares, not Excel, various other softwares, and there you'll be a free bird, and you can study the best fit of your choice. So for practical scenario, nobody can ever say that this particular curve will be best fitted to the given set of data, because the data has been collected. These are observables. So we have observed, we have taken the observation from the system. We do not know the system. So we can just guess, we can just check whether linear curve is fitted or exponential curve is fitted or logarithmic curve is fitted or Gompertz curve is fitted or logistic curve is fitted. We shall give a trial and error method to the set of data with each curve, and the curve which is best fitted, that will be selected. This is the actual approach. I hope I'm able to answer to the problem put forward by the student. Okay, so I hope that he has understood the point. Now, how since I am actually trying to make you learn about the not only the technicality but also the analyticity of this particular chapter, so let us see actually what you need to do. Okay, forget about the examination. To fit the exponential curve, as usual, you have to plot the scatter diagram. You have to check the scatter diagram, and you see the scatter diagram is gives you this kind of structure to the associated with the given set of data. The structure of the count rate with respect to the aluminum thickness, and it is a falling curve. It's has a kind of exponential nature, downward exponential nature, downward falling. So if it seems as if maybe the exponential curve, if we fit the exponential curve, that will be the best fit. Maybe, I don't know. But the question setter is asking me to fit the exponential curve, and then I had to do. But yes, okay, maybe it is possible. But you can easily say that to the given curve, to the given scatter plot, linear curve is never best fitted, or the second degree polynomial is never best fitted. We can easily see from the scatter plot. Okay, so since the scatter plot is showing this kind of decreasing tendency, we shall try with exponential fitting. Now, students often try to remember the normal equations, or when they actually do the statistical calculation, they try to memorize what columns they must introduce to do the calculation. So you don't have to do so. Just remember the normal equation. I have already told you the trick. Remember the normal equation and then study it. See what are the terms we need to calculate. We need summation y star, we need summation x star, we need summation x star y star, and we need summation x star squared. So in your chart, the chart which you are going to prepare, in that particular chart, these columns like y star, x star, y star, and x star squared must be present. The formula actually is telling you what to put inside the chart you are going to prepare to do the calculation. So keeping this in mind, I have prepared this particular table where we already know that my x star is capital X, and the values of x, or if you like to say it as x star, these values are given. So we need summation x star according to the normal equation. So I have calculated it. Y's are given, but this part is blank because summation y is not present in the normal equation. We need a natural logarithm of y, which we named as y star. So I have introduced this particular row. Logarithm of each term has been calculated, and their summation has been also calculated. We need summation x star squared. So each x star has been squared over here to get the summation. And we also need from the normal equation the product of x star and y star. So we have multiplied this variable x star by y star. And all the six observations have been obtained, and their summation has been calculated. After this, we put the values in the respective places of the normal equation, one by one, and we get equation 4 and equation 5. Your next job is to solve equation 4 and 5 by the usual approach, because you know how to solve a linear equation, because this equation 4 and equation 5, they are linear equations in the variable a and b, because the power of the variables a and b are 1. So we are going to solve them for a and b, and we have got this result. Okay, capital A as 8.3953 and b as minus 357.391. Okay, but according to our choice, capital B was indeed equal to small b. So we have got our small b, the parameter small b. But parameter small has not yet been obtained, because we have obtained capital A from the equation. So capital A is this one, which is natural logarithm of small a, and therefore small a becomes exponent of this term, 8.39, which is 4426.21. Once you get your value of small a and small b, you substitute them in equation 1, and we get your exponential curve, which is capital Y equal to a into e to the power bx, that is 4426.21 multiplied by exponent of minus 357.391 into capital X. And there will be obviously a minus sign. It is because you know the curve's tendency is decreasing. If the curve's tendency will be increasing, the exponent, the power present in the exponent will be positive. If it is decreasing, then the power present in the exponent will be negative. So it is quite obvious that the value of small b will be negative. So we have got it. And then using the Excel, I tried to see whether it is indeed coming or not. Now you see carefully that you see the curve, what has happened. The exponential curve fitting has been done. What did I say? Let us check whether exponential fitting is possible or not. Obviously, I am actually referring to the student's question. He may say, sir, is it the best fit? The answer is no, it is not the best fit, because there are fluctuations. Although there are not many fluctuations, but fluctuations are present. This is a kind of fluctuation which is present, and this is a kind of fluctuation which is lesser than that, but okay, that is a fluctuation. Fluctuation is after all a fluctuation, but these points have fall on the curve. So I shall not say this is the best fit, okay, but this is a kind of fit, better than linear fitting and second degree parabola fitting. So we have got our equation 404. This, you see, equation has been calculated, and probably you are seeing that in the value of b has been obtained as minus 344, but here we have got the value as minus 357.391. This happens with the software because software cannot deal with the continuous things. It deals with kind of simulation. So the thing is that when the software is actually considering the discrete points, maybe it is actually considering many digits after the decimal point, and then he is calculating that. So this kind of fluctuations is negligible. You can avoid this kind of fluctuations. These are negligible, but 4426 is coming. Okay, no problem. But according to the question setter, as has been asked from us, that you need to calculate we need to fit the exponential curve to the given set of data. We have done so, but we'll never say that this fitting is the best fit. It is better than linear fitting and second degree parabola fitting. So that is how this exponential fitting is done. After that, I try to deal with this particular problem once again with logarithmic fitting. Okay, and let us see what happens to the logarithmic fitting, what happens to the fitting if we consider the logarithmic curve. Okay, exponential fitting we have done as per the requirement of the question setter, but logarithmic fitting is our choice. Let us fit the logarithmic curve and let us see what is the difference between the two curves. Okay, and then only we can compare which one is the best fit. So I have mentioned here two curves. One is called power curve, a capital X to the power small b, and logarithmic curve, a plus b log x. These are the two forms. You need to know the form of the different curves. If you are dealing with Gompertz curve and logistic curve, then also you need to know their forms. You can, at this juncture, you can ask me this question: why you are considering only power curve and logarithmic curve? Why aren't you showing logistic curve and Gompertz curve? There are two answers to the given question. First of all, showing curve fitting with many curves is beyond the scope of the syllabus. Time will not permit. Second point is that in Excel, if you run this, then you will find that for trend line options, we have several things. Like we have linear, we have polynomial of any degree, we have exponential that has been done right now, we have logarithmic, we have power. Moving average is something else. It is related to time series, and time series is used to forecast business or forecast weather like this. So it is different. But exponential and polynomial and power, no other curve is present over here. Other Gompertz logistics, which I am telling right now, is not available. So I am not showing to the analysis of those curves. Because a few days ago there was a meeting with mathematics department faculty, and I saw there two of the faculties were arguing between them about which software is good for statistical analysis. So one particular faculty, he opted for R statistical software because R is now a fashion. Another is also in fashion nowadays, it's Python. So another faculty went for Python, and both of them were fighting. Okay, we need to buy Python, and someone saying, oh no, we have to include R. Then suddenly another teacher entered from another department, and he said, no, you don't have to consider Python and R. We have MATLAB in Techno India. So MATLAB can very well do the statistical calculation. Then one of the faculties of management department, he was also present. He suddenly raised his hand and he said, we actually do the statistical calculation using SPSS. Then the mathematics faculties, he said, okay, the SPSS has become obsolete nowadays. R is running. R is in vogue. Python is in vogue. Let's deal with that. I was telling, because I have Maple software with me, so I said Maple also can deal with statistical calculation. Another teacher voted for Mathematica. Another teacher voted for Scilab. And there was a huge chaos. But none of us could ever think that whatever software we opted for, the institute or from the personal level, we have to buy it. And buying options is not very catchy, because if you have to shell out tremendous amount of money. If the institute wants to buy it, then he have to bear lakhs of rupees for buying the particular software. Students, even I myself also, for me it is also not possible to buy any software. I am taking your class right now on Zoom, but Zoom, this software, the Zoom, which I'm actually now taking help of, my plan is a basic plan. I couldn't go for the other plans because they need credit card. Net banking is not possible, so I couldn't buy them. So things are not available easily. These things are not handy. None of the teachers mentioned Microsoft Excel, which is handy, and every student has access to that. Microsoft Excel is a kind of software which can deal with statistical problem also. Students, let the student try, let the ball run, and let the student try with Microsoft Excel first. And when he will be in a particular kind of position, at a particular position, and he will have access to other softwares, then he can use them very easily. But right now, every student, every teacher has access of Microsoft Excel. So why not Microsoft Excel? So in Microsoft Excel, since these curves are present, I decided, okay, let us show these curves, the analysis of these curves to the students. And in the syllabus also, they have mentioned curve fitting. And besides that, it is mentioned linear curve fitting, second degree parabola, and general curve. By general curve, what do we mean? They have not mentioned, the syllabus setter has not mentioned by general curve, what does it mean? Does it mean exponential, or does it mean logarithmic, or does it mean an nth degree curve, or does it mean any other thing, converged, logistic? This is vague. What do you mean by general curve? So it is my decision to show you the curve fitting through exponential, logarithmic, and power, because it is present in Excel, and so that you can do the calculation manually, and you can take the help of the software, and you can you can verify your results. That will be a good practice. I hope you all, the students who are present right now in the class, all of you are agreeing with me. Only I have access to a kind of software doesn't mean that every student has an access of that software. Okay. Logarithmic curve. This is the form y equals to a plus b log x, and this particular curve has a kind of form this plus this, so we can easily set the normal equations over there. So just like before, I have the terms of present on both sides of the equation have been preceded by summation, so we get summation y n into a plus b summation log x. In previous cases, I multiplied by capital X. If you remember, in linear curve fitting in the second degree parabola, I multiplied by capital X. In the previous one, in exponential curve fitting, we multiplied by X star. Actually, we multiply by the input variable. And here, you can easily see that the input variable is log X. So we shall multiply both the sides by log X. So we get log xy is equal to a into log x plus b into log x squared. And then we take the summation. Thus we get the two normal equations. As per the requirement of the normal equations, I have prepared my chart. And I'm not going to discuss this in detail because you have already got the hint about what to do and how to prepare the chart. So I have managed my table in this way. I have modified my table in this way as per the requirement that we need, and these things have come. Okay, I have calculated everything manually. I have done this calculation by my hand manually, and after that I have put all the values present in the table in the normal equations, and we get equations in terms of small n small b. These two linear equations can easily be solved, and your values of the estimates of small n small b becomes this and this, and correspondingly your logarithmic curve becomes y equals to a plus b log x. So this is the curve we have fitted. When I applied this, when I took the help of the software, I mean Microsoft Excel, then this came. See what is happening. What did I get? I get minus 4358. Let us check whether it is coming or not. Yeah, approximately same. Minus 4359.74. This is, I think this particular value is much more explicit than this one. This is kind of manipulated, okay, because software has done it, and this has been done by myself. So you see the difference between, but okay, I can treat my minus 4359 as minus 4358, not a big issue. And 970.09 was my value of B. They have got 960, no problem. These are mere issues. But I am again referring to the question said by the student. If he is listening to me, please see that as per the requirement of the question setter, you fitted the exponential curve, and what you got. That is not the best fit to the given set of data of thickness and count of radiation. But when we studied about logarithmic curve, and probably the question setter doesn't know about it, we are able to best fit the curve to the given set of data. Now you can compare this curve. You see all the points are lying on the curve. This curve, this logarithmic curve, if we could use the logarithmic curve earlier, then there was no need to go for exponential fitting. So the main point is that, okay, before I conclude, let me tell you, I started doing the calculation of power curve also. I wanted to see how power curve is being fitted over here, and then I felt very dizzy and very tired, and I stopped calculating and I left it for you. Finish the above analysis with power curve. Okay, I consider power curve is this, and I have set the normal equations for you. You try to do it by yourself and see whether power curve is also best fitted or not, or what is the change among them. Okay. So my point is that you always try to do the problems manually, and you take the help of the software which is easily available to you, and you try to visualize the things, the statistical things from practical point of view. I mean, uh, don't always think that what will happen during the examination. If you can practically deal with that, try to grasp the essence of what you are learning. You are here in this particular module 5, you are actually learning how to analyze curve, and therefore this particular thing is present, curve fitting. I don't know which curve is the best curve. I shall keep on trying. I shall keep on trying on this given set of data, but without removing the yesterday I discussed that you have to scan the data also to identify the outliers and to remove them. So I have to analyze these things properly, and then only I can declare, okay, this curve is best fitted. You take a bivariate distribution from our current situation, COVID situation. Okay, you choose your variables, data of West Bengal and data of centralized data all over the India. Take the two data and plot it in the scatter diagram. Try to fit a curve, linear, second degree, exponential, logarithmic, power. Try to fit and see which one is the best fit. So that is called the analysis. I am here to show you how to deal with the statistical analysis. Examination is not important. Examination comes later on. First of all, what comes understanding. Try to feel whether you have understood the fact or not. Make sure, and then you can do anything, whatever you wish. Okay. So with this, I'm going to conclude my today's session. I hope you have understood, and I'm able to put forward my comments to you properly. On Monday, we are going to meet again with a new topic, which is very important. It is called test of significance. So you can say that this particular topic is actually the course outcome of BSM 301. After that, on Wednesday, we'll be having exam, CA2 examination. So once again, best of luck for that. And then we'll be having Kali Puja, Diwali, and Chhat Puja. And after that, when class resumes, physical or non-physical, we shall be again meeting with the rest of the topics present in the syllabus. So bye for now. Okay, see you soon.